Welcome to the deep dive. Today we're taking a shortcut right into a pretty dense astrophysics paper. We're going deep on radio relics, these incredible arc-like structures you see at the edges of galaxy clusters,
They're absolutely fascinating, and our mission today is to figure out why they've been such a puzzle.
and how some new high-resolution simulations seem to have, well, finally cracked the code.
Right, because these relics are so important. They trace these enormous shock waves from cosmic mergers. But the standard model for how they work, based on something called synchrotron emission, has always had these three huge, nagging problems.
Okay, so let's lay out those three problems, because it's really the whole story here, isn't it?
It is. So, problem number one,
Mm.
the Mach number, which is basically the shock speed, when you measure it with radio waves, it always comes out higher than when you measure it with X-rays.
They just don't agree.
They don't, and they should. Problem two is the magnetic fields inside these relics. They are weirdly strong. We're talking microgas levels, which is way, way stronger than the gas around them.
And the third one is about how they cool. Right. Something about the spectrum.
Exactly. The spectrum tells us how the electrons are cooling off over time, and the patterns we see just don't match our standard sort of laminar flow models. It's like the gas isn't flowing smoothly like we thought.
And this new research says the solution to all three is just the gas being lumpy.
Pretty much. The key ingredient we were missing was upstream density fluctuations.
So the magic isn't the shock itself, but the messy environment it's smashing into. Okay, let's break this down.
So the researchers, what they did is they ran these incredibly detailed shock tube simulations. And the key thing is they added pre-existing turbulence, a lot of choppiness in the gas, just ahead of the shock.
So what happens when this massive shock wave hits that choppy, turbulent gas?
Well, first, the shock itself creates this really dense compressed sheet of material. And when that sheet hits the upstream lumps, the shock front itself gets all rippled and uneven.
Ah, so it's not a single clean line anymore.
Not at all. You get a whole distribution of different Mach numbers all along that one shock front. And here's where it gets interesting. This distribution actually flattens the energy spectrum of the cosmic ray electrons.
Okay, wait. Why is that the critical piece? Why does flattening the spectrum change the Mach number we measure?
Because we calculate the Mach number from that very spectrum. If the spectrum is artificially flattened by this effect, the math just churns. It spits out a higher number. It's a bias. It makes the shock look stronger than it really is, especially for weaker shocks.
So the radio and X-ray discrepancy wasn't an error, it was an observational bias baked in by the physics.
Incredible. Okay,
Right.
but how does that dense sheet solve the magnetic field problem?
It does. That same sheet, downstream from the shock, it becomes unstable, specifically because of the Rayleigh-Taylor instability.
RTI, that's the classic fluid thing, right? When you have a heavy fluid on top of a light one and it starts to churn. That's the one. The dense sheet gets accelerated, it runs into those density fluctuations, and that triggers the instability. It just violently churns the gas, and in doing so, it tangles up and amplifies the magnetic field lines.
And that's enough. That instability can boost the field from, what, almost nothing to those microgauss levels?
The simulations show it can.
Yeah.
It takes the average field from about 0.16 microgauss and pushes it way up, with peaks getting over 2.2.
Oh.
And here's the kicker. Our radio telescopes are most sensitive to the brightest spots, the peaks.
So we're only seeing the extreme tail of the distribution and thinking it's the average.
Exactly. We infer a high average field for the whole thing, even if most of it is much weaker.
Okay, one problem left. The cooling models. The turbulence from RTI must fix that too.
It does. All that churning creates total velocity chaos downstream. So that old, tidy assumption that gas just flows away smoothly at one speed,
Yeah.
that's gone. Instead, you can get older cooled electrons stirred back up and mixed in with the freshly accelerated ones near the shock. And if you're mixing old and new, your simple cooling models are, well, they're just not going to work.
So it all comes together. We've gone from three separate, really baffling mysteries to one single elegant solution. It's all about the turbulence created by a clumpy universe.
It seems to be. But this does leave us with a really provocative thought for you to consider. Many studies suggest that this kind of electron acceleration is only really efficient above a certain speed, a critical Mach number of about 2.3.
Okay.
Well, if the radio signals we see are always biased high, could it be that many of the relics we found are actually below that critical threshold? And if they are, what would that imply about our fundamental understanding of how these incredible structures even form in the first place?